All right, chapter 1, states of matter. This chapter would mostly discuss the states of matter and the perspective we look at them in terms of their minute particles and how they're arranged or they're packed and their motion, stuff to discuss them more in detail, and also about the energy. Now, as far as solids, liquids, and gases are concerned, we usually come up with these kind of pictures to tell our students that how they are arranged. If you take a look at them, then you can talk about the specific stuff that we teach at this level or this syllabus. So let's begin with the arrangement. If you look at the arrangement, you'll find that the arrangement is pretty much regular in case of solids, because you can see them in proper layers. While if we talk about liquids or gases, you would see pretty much of an irregular arrangement, right?
Yeah.
Okay, if we talk about packing, these are too closely packed. We can hardly see any big spaces among them. They're arranged in such shapes that the packing is too tight. In case of packing, we either use the term tight or we use the term close together. In case of liquids, they're not close as the solids were, and the gases are too far away from one another, so much so that the gases can easily move around. Now, if we talk about the particles of solid, remember, the closer the particles are, the stronger the forces of attraction between them. So the stronger forces of attraction would be the case of solid. In the case of liquid, there would be less stronger forces because they are a little bit away from one another. As gas particles are too far away from one another, so the forces of attraction among them would be very less. Remember, any two bodies having mass in this universe can attract one another, all right? So if they're too close, the forces would be strong. If they're too far away, the forces of attraction would be too weak. This is a simple general principle that we teach in physics and further extended in chemistry. So the packing in solid is usually explained in this as close packing. Remember, there is a good hint about it that the packing in solid might be completely different. What's important is that the particles are close together and usually regularly packed. When you draw a liquid, make sure the particles are mostly touching the particles next to them. Right? So if they're touching next to the particles next to them, but at the same time they have some more spaces in them like this, you might have drawn the liquids successfully, right? So this explains the difference how you're supposed to draw solids and liquids. Although most of the time, if you take a look at the past 10 years papers, you would see that the diagrams have not been a part of the question. I mean, they never ask you to draw these diagrams. However, you should know how to draw these in order to understand the differences between them and observe the close differences among them, right? So talking about solids, liquids, and gases, there are other basics that we need to understand. Moving on, the particles in liquid are arranged randomly, so are in gases, but in case of liquids, as we talked about arrangement to be very regular, so they're not random. Remember the words that we use commonly with solids, liquids, and gases. These adjectives and these terms are important. And you should know and memorize these terms so that it's easier for you to come up with the exact words. Most of the time when what I tell my students is to take the words right out of the book, instead writing them in your own words, which may not be scientific enough to explain. The particles in the gas are moving randomly at high speeds in all directions. Now, here we talk about their movement. In gas, the particles are much further apart and there are no forces of attraction. So in this case, what we usually explain is the motion. Let's explain the motion in all these three cases, which is not completely explained in this part of the book. So let me write the motion in case of solids is vibratory motion. We only say that they vibrate. As they are too tightly packed, they can only move a little bit to the right, a little bit to the left, and that's about it. This is the kind of motion that a solid usually does. They do not change their fixed position. So we call it vibratory motion or to and fro motion. In case of liquid, the term that we commonly use in paper is move past one another. They have this much space that they can easily either slide over one another or move past one another. However, in case of gas, as the motion explained in the book is random, however, I would suggest you to use a word haphazard. Do you know what that word means?
No.
No. Okay, haphazard means that they do not care about their own hazard. They move in a straight line, so much so that they collide with another gas particle, or they may collide with the wall of the container and change their direction. They may collide with the lid of the container and may change their direction. We call this motion haphazard kind of motion, a motion in which you do not see the hazard, you overlook the hazard, and a motion in which you keep colliding with other particles, the walls of the container, the lid of the container, so on and so forth. Get the point?
Yeah.
Okay, if that makes sense, you would completely understand that gas particles would keep moving, keep colliding with one another, keep colliding with the wall of the container or the utensil they're kept in, which means the motion is strongest and over long distances in case of gases. And in case of solids, the motion is least because they don't even change their position. So they're just vibrating a little to the left, a little to the right, and that's about it. So the motion is maximum in gases, less in liquids, and least in solids. But remember to come up with these exact terms in case of motion in different kinds of particles. We're explaining you with these terms so that you may reproduce the same terms in exams. Make sense?
Yeah.
Good. So moving on. You can't walk through a brick wall because of the strong forces of attraction between the particles. The particles can't move out of your way. However, you can swim through water because you can push the particles out of the way. Now, it's pretty easy to move through a big gas because there are no forces of attraction between the particles, and you don't even need to push yourself through it. That's the difference. The particles in the solid have less kinetic energy, or they have less movements than the particles in the liquid, which in turn have lesser kinetic energy than the particles in the gas. So the particles in the gas have most kinetic energy. Now, the word kinetic means that they have energy due to motion. Now, as gas particles are moving a lot, they have the maximum kinetic energy in them. Moving to the next point, interconversions between three states of matter. Now, we can change all three states of matter from one to another. Let's go by doing the changing of state between solids and liquids. Now, this one is pretty easy. You probably already know that the solid can be converted into a liquid by the process of melting. The specific temperature at which this occurs is known as melting point, which is also mentioned over here. And if we go vice versa, we can convert a liquid into solid by freezing. The specific temperature at which it occurs is freezing point. For most of the substances on the planet, melting point would be equal to freezing point. However, there are substances which may have different melting and freezing points. All right. But for most of them, it's the same. For example, water melts at 0 degrees centigrade to be converted into, actually ice melts at 0 degrees centigrade to be converted into water, and water can be frozen again at the same temperature to be converted into ice. So instead of using these arrows in chemistry, we use this arrow. This set of arrows represents reversible reaction. Water can be converted into ice can be converted back into water, and that all of that occurs at the same temperature, 0 degrees centigrade. Remember, that's for pure water only. All right.
Yeah.
So for most of the substances, that is going to be the same. However, there can be substances which may have a different melting and freezing point. A good example would be agar-agar solution. All right. Okay, moving on. The changing of state between liquids and gas. Now, in case of liquid, if we give it some heat energy, of course, the liquid is going to be converted into gas, or if the gas is cooled down, it can be converted back into liquid. The process can be boiling, or the vice versa can be condensing. However, at this point, we explain the difference between evaporation and boiling. Do you understand the difference between boiling and evaporation?
Yeah.
So what's the difference?
Boiling is like when it goes from liquid to gas. And then isn't condensing evaporation as well?
No, actually condensing and evaporation are two opposite processes. Okay, let me explain. Boiling occurs at a specific temperature for which we have the name boiling point. Such as for water, that occurs at exactly 100 degrees centigrade. 100 degrees centigrade is actually the boiling point of water. At this temperature, water would be converted into steam. But any temperature in between the melting point and the boiling point is the temperature when evaporation can take place.
Okay,
so if water is converted into vapors at any temperature between 1 to 99 degrees centigrade, it would be evaporation. All right, but only if it occurs at 100 degrees centigrade, it's boiling. Means boiling occurs at a very specific temperature. Any temperature lower than that, even if the substance is being converted from a liquid state to gaseous state, we call that evaporation. So if the water is being converted into vapors at 80 degrees centigrade, maybe at 60 degrees centigrade, maybe even at room temperature 25 degrees centigrade, maybe around 10 degrees centigrade, it's evaporation. All of these are evaporation because boiling only occurs at specifically 100 degrees centigrade for pure water. Remember, we are talking about pure water only. Make sense?
Yeah.
Now, the condensation is exactly opposite. It is when gas is converted into a liquid. Once again, condensation occurs at a range of temperatures. So what we say is that boiling occurs at a sharp temperature, because in case of water, that is exactly 100.00 degrees centigrade. We call it a sharp temperature. However, for evaporation, that occurs at a range of temperatures. Now, as I've given quite a big range over here, that's why I'm using the phrase range of temperatures. And the same thing is explained actually over here in the key point. Evaporation occurs at any temperature, but boiling only occurs at one specific temperature, the boiling point of the liquid. Puddles of water disappear quite quickly despite the outside temperature often being below 5 degrees centigrade in the winter in UK. The water in the puddles certainly does not boil at this temperature. The water evaporates. The water will evaporate at, for example, 5 degrees centigrade, but only boil at 100 degrees centigrade. So this is a pretty good example. And the same thing happens to the rest of the world. It's not just about UK, it's about the rest of the world as well. The water does not boil all day long because the temperature around the world at an average goes from 5 degrees centigrade to about 55 degrees or 60 degrees centigrade, from the cold regions of the world all the way to the hotter regions of the world. So at this temperature, if the puddles are disappearing quickly, despite whatever the outer temperature is, atmospheric temperature is at that point, it's evaporation because it only boils at 100 degrees centigrade. That is the boiling point of the liquid. Remember, we're continuously talking about 100 degrees centigrade because that's the boiling point of pure water. Change the example of the liquid, of course, the boiling point would change and you would come with a new set of instructions or numbers. For example, if we talk about alcohol, as we usually do in most of your book, the alcohol we mostly talk about has a boiling point of around 79 degrees centigrade. So of course, it would boil at 79 degrees centigrade, but any temperature lower than that, even at 78 degrees centigrade, it would evaporate. All right?
Yeah.
Okay. So when we put in the energy breaks the forces of attraction. So much so that the particles spread and they have very weak forces of attraction. That's what heat is used for. Remove that heat, the particles would become slower and would come closer. This can be done by cooling. The energy is taken out. We can say the vice versa has occurred, and that is actually condensation. So the gas condenses back into liquid. All right?
Yeah.
Okay, so moving on. Evaporation is different, as we have discussed. The average speed of particles varies with temperature. Evaporation can actually be easily explained in this diagram. Take a look. There is some sort of liquid contained in a trough, or we can say a tub. Or in this case, you would notice that there are some particles which may leave the surface of the liquid and be converted into vapors in this case. So what do we say? We say that they are evaporated, they are converted from liquid state to gaseous state. Simply speaking, vapors. That's only because if we talk about this particle instead, it is being attracted by this one on the side, this one, the one at the bottom, the one over here. But the ones that are present as a part of the top layer, they might be attracted from here, from this side, but there is nothing on top. So sometimes when they are moving in their own motion, they sometimes surpass the layer of the liquid, leave the layer, and become a vapor. We call that evaporation, which actually occurs at all temperatures between the melting point and the boiling point. But stating these words is not the correct way to state it in exams. I usually tend to ask my students that stating it below boiling point is a good way to write it. So evaporation occurs at any temperature below boiling point. Some very fast particles at the surface of the liquid will have enough energy to overcome the forces of attraction. They will break away to form a gas. This is evaporation. You don't see bubbling. The liquid slowly disappears if it is open to air. If the liquid is in a closed container, the particles would be colliding with one another in the form of the gas, but they won't be able to leave the container, of course, because it's closed. They would be moving slowly enough to be held by attractive forces and will become a part of the liquid later on. So in a closed container, evaporation and condensation will be both occurring at the same time. This is an important line and an important concept in terms of the very few MCQs they sometimes consider for your papers. Get the point?
Yeah.
So in order to further elaborate this point, if I close this entire container like this, for some time, this particle may leave the liquid surface, may become a vapor, but after some time, they may come back to the liquid surface again. So it evaporated, but it condensed. So in a closed container, evaporation and condensation occur at the same time. And if kept for a longer duration of time, it actually occurs at the same rate or the same speed. The number of particles that evaporate from the liquid surface and the number of particles that return to the liquid surface are almost same if the liquid is kept in a closed container for a longer duration of time, which also has been a part of past papers. Make sense? Can you hear me?
Yeah. Someone
Okay.
was in my, what did you say?
I said that the condensation and the evaporation would occur at the same time
Yeah.
and at the same rate, with the same speed, which means
Yeah.
that the particles leaving the liquid surface will almost be equal to the particles that are coming back to the liquid surface in the form of condensation if the liquid is kept in a closed container for a longer duration of time. That's what I said.
Okay.
If it's
Yeah.
clear, we can move on. Can we?
Yeah, it's clear.
Okay, good. So there is another system that we need to understand, and that is sublimation. Sublimation is the conversion of solid directly into a gaseous state. Now, whenever you are supposed to write its definition, which has been a part of past papers, by the way, we use the word directly. Why do we use it? Because this phrase explains it better without involving any liquid in the process. It's because these are specific chemicals which sublime, which convert directly from the solid state to the gaseous state. They don't melt, they don't boil to be converted into a gas. They directly sublime and the solid directly converts into gaseous state, bypassing the liquid state. Hence, we're never able to see the liquid state of these specific components. And the opposite process is known as deposition. Why? Because the gas is converted directly back into solid without going into the liquid state. The process of gas changing into a solid has various names. Sometimes people also call it desublimation, sometimes deposition, and sometimes they simply use the word sublimation again. All these words mean the same thing, so make sure you don't get confused by them, because there are books which would call this one and this one as sublimation. The forward process, the process by which a solid is converted into a gas, is known as sublimation. They might also quote the process of gas being converted directly into a solid as sublimation again. Same thing. However, you may also call it deposition. This occurs to very specific components in your syllabus, and actually, according to your syllabus, we only give you 4 examples. For example, a couple of examples are present over here. An example of a substance that sublimes is carbon dioxide. At ordinary pressure, there is no such thing as liquid carbon dioxide. It turns directly from solid to a gas at minus 78.5 degrees centigrade. Solid carbon dioxide is also known as dry ice because it literally looks like ice. It's just that the ice made from water is wet. However, the ice made from carbon dioxide is dry. And this is what it looks like. If you have ever attended a concert, you would know that the smoke effect is usually taken from this dry ice. There are commonly smoke effects given in stages in concerts. All right. So carbon dioxide converts from solid to gas and gas back to solid. There are a couple of examples that are present in other parts of the book, but not written over here. So I tend to ask my students that you should write all the examples over here so that you can remember them. The next example that is usually quoted in your book is iodine. Iodine, when present in solid form, is actually black in color. All right.
Yeah.
I don't know what happened to my pen, and the writing is pathetic right now. Bear with me, I don't know what's happening to my writing. Okay, when iodine is converted into vapors, then the color slightly changes and it becomes purple. There is a diagram give, I think, of purple iodine vapors after a couple of chapters, few chapters ahead actually. So iodine is a very good example for sublimation apart from carbon dioxide. The other examples in your book consist of ammonium chloride. Ammonium chloride is actually a salt, a white colored salt that can be converted from solid directly to gas or from gas back directly to solid. Remember to either use the word directly in the definition or using the phrase without involving any liquid in the definition. If you don't use these 2 words in the definition isn't considered complete or correct. You won't get the marks. Either use directly or use this phrase so that you can tell the examiner that you understand that it wasn't a conventional solid to gas conversion by melting and boiling. It was sublimation because the conversion was direct and there was no liquid state seen in between. Make sense?
Yeah.
Good. So these were the examples. If you have the book with you, keep noting the stuff down, the extra stuff that has usually been a part of past papers and not written in the book, or is actually scattered throughout the book. Noting them at specific places would help you to get scattered information in an order, and having them at one place helps you remembering or memorizing that stuff for that specific topic, right?
Yeah.
So this is an important point. This is what has been a part of past papers, mostly from this topic, working out the physical state of a substance at a particular temperature. Now remember, there would be 3 pieces of information for this kind of question. What they're going to do is that they're going to tell you the particular temperature, they're going to tell you the melting point of the substance, and they're going to tell you the boiling point of the substance. And then you can easily tell them what is the specific physical state at that specific temperature, particular temperature. Either it is a solid, or that's a liquid, or that's a gas. And there is a pretty simple formula. I think it's written in this book. No, it isn't. Let's write it over here. If the particular temperature, and I'm going to shorten it up as PT, in the question is greater than both melting point and boiling point, the state of that substance is gas. If the melting point, in fact, let's not do it that way. If the particular temperature is less than both melting point and boiling point, that particular substance is a solid. And if the particular temperature given in the question is greater than the melting point, but is smaller than the boiling point, that particular substance is liquid. Let's take an example. Here, the room temperature is the particular temperature, and that's 25 degrees centigrade probably, all right? In this case, it feels like it has been picked up as 20 degrees centigrade. Doesn't matter. In the question, they're going to give you exact temperature you need to work it. Now, oxygen is a gas at this temperature because this particular temperature is bigger than both its melting point value and the boiling point value. Water is a liquid at this temperature, or in this case, I don't know, bromine is a liquid at this time. In this case, why? Because the melting point is smaller than this room temperature and the boiling point's value is bigger. In case of lithium, the melting and the boiling point are both bigger than the room temperature, hence that's a solid. Make sense?
Yeah.
Let's practice it a little bit. Let's practice it with some unknown substances. Let's say I'm going to give you the particular temperature. I'm going to give you the melting point. I'm also going to give you the boiling point, just like in your past paper questions. Let's say the substance is X. The particular temperature at which you need to find out is 100. It melts at 79 degrees centigrade while it boils at 119 degrees centigrade. What should be its state of matter at this particular temperature? 100.
Liquid.
Good. What if I need to measure it at 25 degrees centigrade, the same substance?
Then it's gas because it's smaller.
Good. And I heated this substance up at 1000 degrees centigrade. What would be its physical state then?
Gas.
So it's a gas at 25 degrees centigrade, and it's also gas at 1000 degrees
Right.
centigrade.
Oh, yeah. Wait, won't it be gas if it's bigger than its melting point and boiling point?
If the particular temperature is bigger than its melting and boiling point, then definitely it would be a gas. But if the particular temperature is smaller than the melting and boiling point, it would be a solid.
Yeah.
See, at 25 degrees centigrade, it would be a solid. Heating it up to 79 would make it melt, and at 100 degrees centigrade, it would actually be a liquid. Heating it more up to 119 degrees centigrade would boil it, and it would be converted into its gaseous state. Hence, at 1000 degrees centigrade, it would be a gas. So if the particular temperature is bigger than both of these values, it's a gas. If this temperature is smaller than both of these values, it's a solid. And if this temperature is right in between these two values, I mean, bigger than the melting point and smaller than the boiling point, it is actually a liquid. Now, this whole practice is pretty easy as you were able to answer it correctly. But this becomes a little bit tricky once we have the values of melting and boiling point in negatives, right? This is where it becomes difficult. For example, let's take the example of oxygen over here. You would see that the boiling point is around 100 minus 196, and the melting point is around minus 221, I guess, or somewhere around it. I guess it's 219, negative 219. So here comes the part where we need to discuss it differently. Let's take the same example. Let's take the example of oxygen. It's O2. I'm not going to tell you the particular temperature at first. Let's just write the melting and the boiling point. The boiling point is negative 196 degrees centigrade, while the melting point is negative 219 degrees centigrade as far as I remember. I might be incorrect, but it would definitely serve the purpose of asking the question. Okay, so what if the particular temperature is 25 degrees centigrade, let's say room temperature? What would be the physical state then?
Gas.
Negative 100 degrees centigrade?
It would be liquid. Actually, I'm saying
Think again. Think again. Then give me.
it would still be gas.
Good. Now you're correct. Okay, what about negative 200 degrees centigrade?
It would be liquid.
And why is that? First, you're correct.
Because
second, why?
It's less than the boiling point, and it's more than the melting point.
Right, very good. It's more than the melting point. Why? Because negative 219 is a smaller number, and negative 200 is actually a bigger number. However, it's less than the boiling point still. Why? Because negative 200 is a smaller number, and negative 196 is a bigger number as per maths. Because in mathematics, in negatives, the bigger becomes smaller and the smaller becomes bigger. Opposite to the contrary, the positive working. So this is the part which confuses the student most, as there are negative signs usually there. If the whole working is done with positive signs, it's pretty easy for the student. Remember this specific formula to get your answers correct. It would work correctly every single time.
Yeah.
I hope you have written it.
Yeah.
Good.
So we're done 1.1. So I think we move to 1.2 now.
Sure.
We've done 1.2 as well. So I think we move to 1.3 and then 1.4.
Sure, we can. And 1.3s.
1.3 is understand how the results of experiments involving the dilution of colored solutions and diffusion of gases can be explained.
Okay. So I shouldn't be moving to the next pages because this is diffusion. Okay, so diffusion is spreading of the particles from there at a high concentration to where there are in lower concentration. Actually, this one is a higher concentration, while the particles are concentrated at a smaller place. In a lesser volume, in a lesser space, there are more number of particles. They move and spread into a way in which they are in low concentration, in which By that I mean, in a certain volume, there are fewer particles present. Take a look. You may count the number of particles in this volume, and you may count the number of particles again in this volume. This one would have a higher concentration, this one would have a lower concentration. All right, this only explains the phenomenon of diffusion. This does not explain the result. Okay, so what's the result? What happens at the end?
They spread out.
They spread out.
So there's a lower concentration.
Continue.
So it goes from high concentration to lower, and then there's like, it's just more spread out. It's the same number of particles.
Let me write a phrase which works every time getting the complete marks. This is what happens at the end. This is the before section of this experiment or explanation. This may be the after section, but if you look closely at the entire picture of after section, you would understand that they have spread evenly throughout. So diffusion carried on, the process carried on until there has been spread out equally throughout the container. The same thing is written over here in the words right below the diagram, which can be actually summarized in this phrase. Writing this phrase would get you complete marks if they're talking about the resultant of diffusion, the result of diffusion. For example, let's think about this one. Bromine vapors are red-brown in color. Air, on the other hand, is colorless. The two gas jars actually can be toppled, or we can simply take the lid out of it. So the bromine would start spreading and moving towards the lower concentration region. At the same time, the air would start moving towards its lower concentration region. What would happen at the end? The colors would spread evenly throughout both the gas jars. Right?
Yeah.
Okay. This experiment can be performed with a different colored gas. We can perform it with nitrogen dioxide, which also happens to be brown in color. They may perform it with any other colored gas. Don't worry, if they change the gases, doesn't matter. You simply are supposed to focus about the movement of particles in terms of diffusion, or what would happen as an end result. Now, the experiment that you usually see happen a part of past papers way too many times. Okay, this is the part where they consider ammonia, which is a gas, hydrogen chloride, which is another gas. They react to form a solid, which is ammonium chloride, the one we just discussed for sublimation example, right? This is ammonium chloride, the same one I just discussed a few moments ago. Okay, yeah. But here we're not considering it sublimation. We are actually forming it with a reaction between ammonia and a reaction between hydrogen chloride. What do? We take a long glass tube, open at both ends. We soak in cotton wool, one in concentrated ammonia solution. We put it on one end. On the other, we have the cotton wool soaked in the concentrated hydrochloric acid solution or hydrogen chloride. Actually, hydrogen chloride is a gas which is dissolved in water to get the hydrochloric acid solution. So it has the same formula over here, right? This one is also soaked in HCl. Now, the gases would diffuse from this point to this point. This experiment sometimes in past paper questions is also marked in such a way that they discuss is at the total of 0 to 100 centimeter. In such a way, this travels 59.5 centimeter. I'm taking an example of an exact past paper question, and this seems to be traveling like 40.5 centimeter then. If you're done with the rest of the book, you may be able to understand that this is a lighter gas and this one is a heavier gas. This one's heavy and this one's light. Do you know why ammonia is lighter and hydrogen chloride is a heavier gas?
Why?
This has everything to do with the moles chapter.
Oh.
Have you studied it enough to understand the reason? It has nothing to do with diffusion over here.
Not really.
Are you able to calculate their molar masses, MR? We
Yeah.
usually depict it as
Yeah.
MR from the periodic table.
Yeah.
Now, if you look at the periodic table, nitrogen, the value for nitrogen is 14. The value for hydrogen is 1, but it has to be multiplied by 3. Why? Because there are 3 atoms. The total would come around to be 17 in this case, all right? If we do the same kind of working from the periodic table, hydrogen is 1, chlorine turns out to be 35.5 in the periodic table. Add them up, the answer would come out to be 36.5. Now, if you look at both of these values, you would find that the ammonia is lighter because it has a mass of 17, and hydrogen chloride is heavier because it has a mass of 36.5, which explains the difference in the distance they have traveled. So it can give you a pretty good result over here. Lighter gases travel faster than the heavier ones. I try to tell it in a common joke in my classes that fat people run slower and actually the slim ones can run faster. I'm not targeting any specific people, or I'm not doing a stereotype, but just to explain. All right. So the lighter gases travel faster and the heavier ones travel slower. Just not gases, it actually is applicable to all the molecules. The lighter ones will travel faster and the heavier ones will travel slower, in such a way that if we go by with a timed experiment, the lighter ones will travel more distance as compared to the heavier ones. Like in this one, it does. Okay. And the white smoke produced over here, that the white ring tells us that they both have reacted and produced ammonium chloride, which actually forms in the form of white smoke. Clear enough?
Okay, so yeah, so that's 1.3 done as well. So the next one is 1.4, which is solvent, solute solution, and saturated solution.
Okay. Now this is about the solute, solvents, and solutions. I hope you're clear with solute, solvent, and solution, the basic definitions. Okay. Before I go with saturated and the ones, I need to explain all the types. Students tend to understand only the types that are given over here, but it's better to understand all types because those are going to help us later in the book. Now, to begin with, I hope you are already familiar with the first two types I'm going to write over here, soluble and insoluble solutions. Are you familiar with those?
Yeah.
Soluble solution is a solution in which the solid can be dissolved into the liquid, or the solute can easily be dissolved into the solvent. However, the insoluble is the exact opposite term, in which the solute is not cannot be dissolved in the solvent, right?
Yeah.
Okay. You might also be familiar with these two. However, these two are relative terms.
Yeah.
Are you familiar with these two?
Yeah.
Dilute means a solution in which the amount of solute is far less than the solvent. Concentrated is the exact opposite. The amount of solute is much more in comparison as to the solvent. Actually, dilute and concentrated are relative terms. You cannot tell for one kind of solution that it is actually dilute or concentrated if you do not compare to another solution of the same kind. Let's say we have water, and in both the beakers, the water is 100 cubic centimeter, right? So it means we have the same amount of the solvent. Let's say we have 1 tablespoon of salt in, let's say it's just 1 tablespoon. I'm going with very easier terms. And actually we have used 2 tablespoons of salt in the other one, right? The normal salt we eat every day, which is, by the way, sodium chloride. We would need to discuss it a lot throughout the book. So which one do you think is dilute and which one's concentrated?
So dilute would be the one with with more sugar, and then concentrated will be the one with less.
Salt, actually it's salt.
Yeah,
Sugar
so
is different. Okay, so 2 tablespoons actually is concentrated, and this one is dilute. Dilute has smaller amount of solute, and concentrated has a larger amount of solute. In this case, the solute are these tablespoons, and the solvent are is this water. All right. So that's how dilute and concentrated are explained. So once again, let me repeat, this is a relative term. In relative terms, you need to compare one solution with the other. You cannot tell ultimately, if you get only one example, let's say if I get only one example of this sort, I cannot call the solution as dilute or concentrated because it has to be compared with something. However, in papers, sometimes they, as a part of the question, do write a solution as dilute or concentrated. It is actually to save the time for the student by giving them a piece of information so that they don't have to compare it with anything else. All right. So in questioning papers and exams, the questions might contain the word dilute and concentrated. It is for you to understand and not get confused that you need to compare it to something. Get the point?
yeah.
Now, there is another term that we use, which is much like the first term, miscible and immiscible. Do you understand what these terms stand for?
I think I have an idea, but I kind of forgot now.
Okay. Soluble and miscible almost means the same thing. The only difference is that soluble is actually solid plus liquid solution, in which solid is the solute and liquid is the solvent. Miscible is actually liquid plus liquid. So if we are mixing water and oil, that would be an immiscible solution. If we are mixing, let's say we are mixing soda and milk, let's say we're mixing water and coffee, water or tea, water or milk, this is a liquid-liquid solution. We use the word miscible for it, not soluble. Remember, the word soluble is for the solid when dissolved in liquid, and miscible is when liquid is dissolved in liquid. Immiscible is for the same purpose. It's just that when they are not, you cannot dissolve one into the other, we call it immiscible. Like you cannot dissolve water into oil, but you can definitely dissolve water into alcohol.
So immiscible is where you can't mix liquid and liquid.
Yeah, miscible is when you can mix liquid and liquid, and immiscible is when you cannot mix two liquids. Remember, the difference between soluble and miscible is that here is a solid involved, but it is made up of both liquids in case of miscible. All right?
Yeah.
Okay, good. The last term would be of 3 types: saturated, then we have unsaturated. Something that is not explained over here but comes as a later part of the book is supersaturated. So I'm going to go with 3 definitions instead of 2. All right?
Okay.
Okay. Can you explain saturated to me? Do you have an idea?
Oh, will it be there's more solute in?
Yeah, definitely. In fact, these words are very good in explaining that. There are some specific terms he has used over here. Maximum amount. So yeah, we definitely use a lot of solid. Okay, let me tell you an example that can commonly be performed at home. You don't need to go to lab in order to perform it. The glasses we commonly use at home are usually of 250 cubic centimeter, 250 ml glasses that we use commonly at home to drink water. Even the mineral water bottles come in the same size, 250 cubic centimeter. In this much amount of water, which is actually like 1 glass of water, in this much amount, if you're adding a tablespoon, a eatable tablespoon, and this time we're taking the example of common white refined sugar that we commonly use at home, you would easily be able to mix 3 tablespoons of sugar in this volume of water. The first one would be dissolved easily. For second one, you might have to stir a little. For the third one, you might have to stir for a little bit more time. like 10 to 15 minutes before it can be dissolved, right?
Yeah.
And that's the maximum amount of sugar you can dissolve at home at the room temperature for water, for this amount of water. So if the maximum amount has been dissolved, and that is 3 tablespoons, right?
Yeah.
We call it a saturated solution, because whatever amount that was dissolved in, that was the maximum amount. You cannot dissolve any more at that particular temperature. So saturated is 3 tablespoons in this example, all right?
Yeah.
So what would be unsaturated? Anything less than 3 tablespoons would be unsaturated. 1 tablespoon would be unsaturated. Why? You can dissolve 2 more. 2 tablespoons would be unsaturated. Why? You can dissolve another spoon. 2.5 tablespoons would be unsaturated. Why? Because you can dissolve half a tablespoon more. So anything less than 3 tablespoons would be unsaturated. Why? Because you can always dissolve more at that particular temperature. Remember, this part of the definition is very important. And what if you try to dissolve more than you actually wanted to? Then that would be known as supersaturated. If you want to surpass this 3 tablespoon limit, that kind of solution would be known as supersaturated solution. Remember, heating is required in this case. You must have tried.
Can you
tried.
say the definition for supersaturated again, please?
I haven't stated the definition. I'm trying to explain it word. First, I'll define it later. When you can understand or grasp the whole thing, then I'll define it and you would find the definition way easier to understand. So what I'm trying to say over here, you need to go with a little bit of heating in this case, because you want to surpass this 3 tablespoon limit. So what happens, you might have tried Arabian sweets. Arabian sweets are too sweet. How come they can come up with too sweet criteria? Definitely they have dissolved a lot of sugar. This happens by heating the solution. So don't do it at 25 degrees centigrade if you want to go higher than this one. So at 25 degrees centigrade, you can only go with 3 tablespoons. Take it closer to the boiling point, like 90 degrees centigrade. Let me tell you, you would easily be able to dissolve 6 tablespoons of sugar. Easily. Why? We went on with heating the system, you were able to dissolve more and more.
Is it because when you heat particles, they go farther apart, so there's more space for the solute?
Exactly. Plus, they have more energy to get the substance dissolved. Dissolving requires energy. When the particles don't have enough energy, they're unable to dissolve any more solid that we're going to throw in the liquid.
Yeah.
So after giving them heat, we actually give them energy to dissolve more and more. All right, that is supersaturated. The easiest way to define supersaturated is when you are able to dissolve more than the amount of saturated solution, more than what you dissolved in saturated solution, by going at a higher temperature or by heating the system.
Yeah.
Now, this definition would be very easy to understand as you've understood the whole procedure by a simple example that you can perform at home.
Yeah.
Which brings us to the definition of solubility. So the solubility of a solid in a solvent at a particular temperature, remember these words are very important every time, is usually the mass of solute, which must dissolve in 100 grams of solvent at that temperature to form a saturated solution, which means the maximum mass of solute that we can dissolve in 100 grams of solvent. All right?
Yeah.
And why are we using the word at a particular temperature? Because as soon as we change the temperature, the mass of solute can be changed. As soon as we change it from 25 to, let's say, if you take it from 25 to 35, this mass of 3 tablespoons would change. From 35 to 45, there would be another change. From 45 to 55, there would be another change. Approximately half a tablespoon change is present at every 10 degrees centigrade. So from all the way from 25 to 95, you're able to add 3 more tablespoons, 3 tablespoons before, 3 more after. That's why. Which explains that the solubility comes with at that specific temperature words or phrase in its definition. Now, the topic doesn't just stop over here. They have some few examples and investigations that we need to understand for our papers. The maximum mass of solute that dissolves in 100 grams of solvent at a particular temperature, for example, sodium chloride, dissolves about 36 grams per 100 grams of water at room temperature. So this is the very good example of a saturated solution, as they have quoted the exact amount. Now, we can easily investigate solubility. For example, we can use to measure the solubility of potassium nitrate in water at 40 degrees centigrade. The steps are pretty easy. Weigh an evaporating basin, heat a boiling tube of water to just above 40 degrees centigrade, add potassium nitrate to water in the boiling tube, stir rapidly until no more of it will dissolve, and there is some undissolved solid left over. This makes sure that all of it has dissolved. Allow the solution to cool at exactly 40 degrees centigrade. Pour some of the solution into an evaporating basin. Now, this is important that you only pour off solution and no solid. You do not have to pour all of the solution, just some of it. Weigh the evaporating basin and its contents. Heat the evaporating basin and contents gently to evaporate all of the water. When it looks like all of the water has evaporated, weigh the contents again, basin and the contents, of course. Now heat the evaporating basin and then reweigh. Make sure you do these steps, step 8 and 9 again and again until you get constant mass. Now this figure explains the whole thing. So we have water which we have heated. It's known as a water bath, in which we have the boiling tube, a thermometer set, and some potassium nitrate is thrown into a specific amount of water. Now we cool it exactly to 40 degrees centigrade, pour off some of the solution. We put it on the evaporating basin. This has a higher mass. We keep heating it until it comes to a constant mass. There comes the part where we need to calculate. Let's go with the calculation. Do you understand the steps here?
Yeah.
Now, these steps will make more sense once you get to the calculation. The calculation is actually the mass of empty basin, which is 25.72 grams. Now, the basin plus the solution is 58 grams. Now, this value can be different for different students. That doesn't matter. Once mass of evaporating basin and dry crystals are taken, then you can calculate the mass of water and the mass of crystals. Now, these two values would be same for most of the students if done correctly. What you're supposed to do is to get the solubility. Mass of solute is put as a numerator. The mass of solvent of water is put as a denominator. Divide them, multiply them with 100. You'll get the solubility of specific solute, which in this case is potassium nitrate, with a specific solvent in 100 kg mass, which is water in this case, and you get the solubility values. Remember, this is the solubility value at 40 degrees centigrade. So this part is very important. As soon as you change the temperature, the solubility value would change, which is further explained in the next topic, which has been a part of past papers too. This is usually a very good question for past papers. This question consists of a graph. When we plot the changes with temperature of solubility of solids, which actually changes as you increase the temperature, the solubility mostly increases, we call it a solubility curve if we plot it on a graph. Take a look. The same KNO3, potassium nitrate, is put over here. Starting from 10 degrees centigrade all the way to 90 degrees centigrade, you would notice that somewhat from 20 grams, it went all the way to around 180 grams, maybe. Yeah, around that. 190 actually. Okay. So this dissolves in this specific temperatures. The question related to solubility curves are to evaluate from the graph. I hope these lines which I have drawn are commonly known as extrapolation in mathematics terminology. You might be asked to do the same in exams. For example, they may ask you at 50 degrees centigrade, how much amount of potassium nitrate was dissolved in water? this much amount of water. So I hope you understand at 50 degrees centigrade, you are supposed to extrapolate these values like this and get the value over here. This is known as extrapolation.
Yeah.
I hope you already know how to do that.
Yeah, I do.
Good, good. So if you take a look at these curves, you would find that a lot of amount of potassium nitrate is capable of dissolving in water if it is compared with potassium chloride, which actually is dissolved in much smaller amounts in comparison. Take a look at 90 degrees centigrade, only a small amount of it is soluble, like around 50 grams or so. All right, so different solids show different types of curves. One part that is very important is this last line in this paragraph. Remember, let's say we took potassium nitrate, we went from 10 degrees centigrade all the way to 90 degrees centigrade over here. We were able to dissolve from 20 grams all the way to somewhat around 190 grams of it at this temperature. We brought it back from 90 degrees centigrade to 50 degrees centigrade, right? Some of the salt would crystallize out of the solution. We also use the word precipitate out of the solution, and you can always measure it. That has been a part of past papers. How? Let's take a look. At 90 degrees, we have already extrapolated the value to be around 190 grams. At 50 degrees, we extrapolated the values to be around 80 grams, let's say. Let's suppose it was 80 grams. How much would be the amount of salt that crystallizes out? It's pretty easy. 190 grams minus 80 grams, the value would be 110 grams.
Yeah.
This kind of question has been a part of past papers, and it's pretty easy to solve from the graph. No matter what kind of temperatures they come up with, you should know the crystallized amount would be what by extrapolating from the graph. Let's say they went down from 70 degrees centigrade all the way to 35 degrees centigrade. What would be the amount of salt that crystallizes out in grams? You can always calculate that, right? By extrapolating two values and then subtracting them.
Yeah.
Okay, good. If you can do that, I think we should be moving on. Do you have a question?
Yeah. So after this, after 1.10, the one, I mean 1.7, the 1.4 with the one we did, we move on to 1.14, which is know what is meant by the terms atom and molecule. It's basically atomic structure.
Oh, so that's not this chapter, that's the next one, actually.
Yeah, so this chapter is finished.
So yeah, this chapter is finished. Just a